Problem of points, also called the problem of division of stakes, concerns a game of chance where both players have an equal chance of winning each round. Both players contribute equally to the prize pot. The winner of the pot must have won a certain number of rounds to collect. The problem of points asks how the pot is to be divided if the game is interrupted before one of the players wins. Intuitively, you might say that the division should somehow depend on the number of rounds won by each player, so that the division of the prize pot favors whoever was closer to winning. The problem arises when you have to decide what fair division actually means based on the game. Let's start with an example to demonstrate. Let's say player A rolls a 6-sided die and player B rolls an 8-sided die. Whoever rolls the higher number gets the point. If they both roll the same number and tie, then player A gets a point. The first player to get to 10 points wins the game. What is the probability that player A wins the first point? First, let's make a table of all possible roll combinations from player A and B. There are 6 times 8, 48 possible combinations of rolls. The highlighted combinations are the scenarios when player A wins the point, of which there are 21 cases. So the probability that player A wins the first point is 21 over 48, which can be reduced to 7 over 16. Subsequently, what is the probability that player A wins the game? If player A is to win, they have to roll a number greater than or equal to player B's roll, 10 times. We found out that there is a 7 over 16 chance of player A winning a point, so player B who wins when player A doesn't has a 1 minus 7 over 16 chance of winning a point, which is 9 over 16. Player A needs to win 10 points to win the game. Player B can of course also win points, but to calculate the probability of player A winning, we discard the scenarios where player B wins 10 points before player A. There are still many ways that player A wins 10 points before player B. Player A could win 10 points in a row. The chances of that happening are 7 over 16, which is the probability of player A winning a point, taken to the power 10. Then there is the scenario that player B wins 1 point in one of the rounds. In this case we still take 7 over 16 to the power 10 for the 10 points player A needs to win the game, but we also multiply it by 9 over 16 to the first power, which is the probability that player B takes 1 point before player A wins the game. However, we also have to consider the possibility that this 1 point that player B wins can happen at any round. Player B might have gotten a point in the first round before player A won 10 consecutive points. Or maybe player B won in the second round, or the third, or the 10th. We can lump all of these possibilities together into one scenario where player B wins 1 point to player A's 10. To account for all of the possibilities, we can multiply the probabilities by 10 choose 9, which basically means that in the 11 rounds played, it takes player A 10 rounds to win enough points to win, and 1 round where player B takes a point. We subtract 1 from the 11 rounds total because we don't need to consider the final round played where player A earns the last point they need to win the game. Of that we choose 9 since we are considering the combination of the 9 other points that A wins. We can apply this logic to the other scenarios where player A wins the game. The scenario where player B wins 2 points before player A takes 10 points has the probability 7 over 16 to the power 10, times 9 over 16 to the power 2 for the 2 rounds won by player B multiplied by 11 choose 9 since there are 12 rounds played and 11 considered since the final point is earned by A as a condition of winning. And again we can do the same for the scenario where player B wins 3 points and 4 points and so on until player B wins 9 points and player A wins 10 to win the game. A pattern starts to emerge and we can use it to rewrite the probability of player A winning as a sum from a minimum of j equals 10 rounds played to a maximum of 19 rounds. The combination is the total number of rounds given by j minus the final round, choose 9 multiplied by 7 over 16 to the power 10, times 9 over 16 to the power of the number of rounds where A doesn't win a point, j minus 10. This comes out to something like 0.2897, which you can check using Wolfram alpha. Now suppose that in order to win, player A only needs 7 points to win while player B needs 9 points. Now what is the probability that player A wins? Note that the probabilities of winning a point haven't changed, only the number of points needed to win the game. We can modify the summation from earlier. J will start at 7 since that is the minimum number of points player A needs to win the game. And the upper round is 7 plus the maximum points player B can take without winning the game, which is 9 minus 1, giving us an upper bound of a maximum possible 15 rounds. Then we consider the combination of the first 6 points in the total rounds played, discarding the final round which goes to player A, multiplied by the probability of player A winning a point for 7 of the rounds and not winning in the other rounds. The probability comes to something like 50.8%. Let's go back to the 10-point game from earlier and look at the problem of points in the game. Suppose both players wager $1 and the winner, the first to get to 10 points, keeps the $2. Also suppose that in the first 8 rounds, player A has won 6 of the rounds and player B has won 2. If the game is interrupted now, how should the $2 be split up based on each player's probability of winning the game? To answer this question, let P sub 4, 8 denote the probability that player A wins, if they need 4 more points and player B needs 8 more points. Then player A's share of the pot is the expectation of the money won by player A, given that the current score is 6-2. This expectation is the sum of the scenario where player A wins and the scenario where player A doesn't win. This can be written as the payout if player A wins times the probability that player A wins given the current score plus the payout for player A if they lose times the probability that player A loses or player B wins given the current score, which can be rewritten as the $2 payout for winning times P sub 4,8. And from the previous questions we answered, we can come up with an equation to find that probability. The sum will be from j equal to 4, which is the number of points player A needs to win the game, up to 4 plus 8 minus 1 equals 11. Then the combination of j minus 1, choose the next 3 points player A needs, multiplied by 7 over 16 to the power the number of rounds player A has to get a point, multiplied by 9 over 16 to the power the rounds that player A doesn't win a point. So to generalize, let player A needs m points to win the game and player B needs en points to win the game, and P is the probability of A getting a point and Q is 1 minus P, the probability of A losing the point to player B. Then the expectation is the payout times the sum from j equals m to m plus en minus 1 for the combination j minus 1, choose m minus 1 times probability P of A winning a point to the power m, which is the number of points A needs, times 1 minus probability P, which is the probability of player A losing the round, to the power j minus m. This should be recognizable as the negative binomial distribution. This is the problem of points with 2 players. But what if we have 3 players playing the game? Let's start with an example and build to a generalization. Let's suppose there are 3 players, A, B, and C, who are equally likely to win a point in each round of the game. They agree to play until one of them wins some number of points. Say that the game is interrupted with player A needing 1 point to win the game, and players B and C each needing 2 points to win. How should the stakes be divided? Since we know A, B, and C are all equally likely to win a point each round, the probability is 1/3. The scenarios where A wins are as follows. Player A wins the point in the next round, the probability is 1/3. Player B or C wins the point in the next round and player A wins the round after that, the probability is 1/3 times 1/3. 1/3 squared for both cases. Player B or C wins the next round, then whoever of them didn't take the point this round, wins the following round, then player A wins the round after that, winning the game, the probability is 1/3 cubed in both cases. Then the player A's proportion of the stakes is a sum of all of these probabilities, giving us 17/27. Players B and C are lacking the same number of points, so we can take the remaining proportion of the stakes and divide it between players B and C, with them getting 5/27 each. To generalize, let's say players A, B, and C have probabilities P, Q, and are of winning a round and need I, J, and K points to win the game. Recall that when we had 2 players, we could use negative binomial distribution to find the probability of one player winning the game. So when there are more than 2 players, we can use That is all. Thank you.